One ordinary star lost nearly a fifth of its light, without warning, without a schedule, and without any obvious object passing by. For a moment, astronomers faced a possibility that sounded less like science and more like science fiction. Someone might be building around it. The star is officially called KIC 8462852, but the world would come to know it by a far more memorable name, Tabby's star. Sits in the constellation Cygnus, roughly 1400 light-years away, appearing completely unremarkable through an ordinary telescope. It is an F-type main sequence star, somewhat hotter and more massive than our Sun, with no obvious reason to behave strangely. The mystery began with NASA's Kepler Space Telescope, a machine designed to watch stars with extraordinary patience and precision. Kepler searched for planets by measuring tiny, repeated decreases in starlight whenever an orbiting world crossed in front of its star. A normal planet produces a clean rhythm, a shallow dip, a recovery, then the same dip again after one complete orbit. But when volunteers from the Planet Hunters project examined this star, its light curve looked nothing like an ordinary planetary transit. The brightness fell at irregular times, in irregular shapes, sometimes for days, and once by more than 20%. That is enormous. A giant planet like Jupiter crossing a Sun-like star usually blocks only around 1% of its light. Kepler's instruments were checked, nearby stars were compared, and the conclusion was unavoidable. The strange signal was genuinely coming from space. The star was nicknamed after astronomer Tabitha Boyajian, whose team formally described the anomaly and tried to explain the impossible-looking pattern. Some dips were smooth, others contained jagged structures, overlapping shadows, and sudden recoveries, as though many objects crossed together. And most importantly, the events did not repeat on a clear schedule, making a single ordinary planet an extremely poor explanation. Researchers considered stellar pulsations, magnetic activity, eclipsing companions, instrument errors, and young star behavior, but none comfortably matched every observation. One promising natural idea involved a vast family of exocomets, broken into fragments and trailing enormous clouds of dust. If those fragments crossed our line of sight in clusters, their dusty tails could create complicated, uneven shadows across the star. But the amount of material required seemed extreme, and the system showed little of the warm infrared glow expected from abundant nearby dust. Another possibility was a collision between planetary bodies, producing a temporary storm of debris large enough to hide part of the star. Yet a violent collision should also create heat and infrared radiation, and astronomers did not find the strong excess they expected. Then a far more provocative idea entered the discussion. Perhaps the shadows were not natural objects, but structures built by intelligence. In 1960, physicist Freeman Dyson argued that an advanced civilization might capture a major fraction of its star's available energy. He did not simply imagine one rigid shell. A vast swarm of orbiting collectors could also intercept starlight and re-radiate waste heat. To distant astronomers, an incomplete Dyson swarm might appear as irregular pieces crossing a star, producing deep and unpredictable dimming. Tabby's star offered the silhouette people had imagined for decades, and the alien megastructure story spread around the world. But an exciting possibility is not evidence. Scientists needed signatures that could distinguish engineering from dust, planets, or unusual stellar physics. One expected clue was infrared waste heat. Any technology absorbing vast amounts of starlight would eventually need to release energy somewhere. Observatories searched, but no compelling infrared excess appeared that would support a civilization capturing a large fraction of the star's power. Radio telescopes also listened toward the system, searching broad frequency ranges for persistent artificial signals, but reported no convincing detection. That silence did not prove nobody was there. It only meant the specific observations found no signal strong enough to identify. Then the mystery changed again. Researchers discovered that Tabby's star was not only suffering brief dips, but also slower brightness changes. Across Kepler's 4-year watch, the star gradually faded, then experienced a sharper decline, adding another timescale to the unexplained behavior. Was one mechanism producing both the quick shadows and the slow fading, or were several unrelated processes happening in the same system? In 2017, the star began dipping again, giving astronomers something Kepler's archived data could not provide, a warning while events were happening. A global observing campaign followed the star through multiple new dips, which researchers informally named Elsie, Celeste, Skara Brae, and Anchor. Telescopes measured the fading through different color filters because the color of missing light can reveal what is blocking it. The result was crucial. Blue light was generally reduced more strongly than red light during the observed dimming events. A large opaque object should block visible colors almost equally, like a solid wall moving in front of a lamp. Tiny dust grains behave differently. They scatter shorter, bluer wavelengths more efficiently, leaving a color fingerprint in the fading starlight. That fingerprint strongly favored fine, partially transparent dust and worked directly against the idea of large, solid alien structures. Measurements suggested grains smaller than a micrometer in important parts of the obscuring material, almost unimaginably tiny cosmic particles. Yet this answer created a new problem. The intense radiation pressure should quickly push such grains away from the system. If the dust disappears within months, something must repeatedly produce or replenish it, turning the mystery into a search for a cosmic factory. Perhaps comets are continually breaking apart near the star, releasing fresh dust each time their stretched orbits bring them close. Perhaps a larger body was shattered, leaving fragments that collide, crumble, and feed new clouds along a highly eccentric orbit. Models show uneven dust distributed around such an orbit can reproduce portions of the short dips and longer fading. But no single dust model has yet explained every depth, duration, shape, color change, and long-term trend without difficult assumptions. Even the absence of strong infrared emission is tricky because cold or distant dust can remain faint at the wavelengths already observed. Other researchers have explored dust between the star and Earth, ring systems, disrupted moons, or changes originating inside the star itself. Intrinsic stellar explanations remain difficult because Tabby's star otherwise resembles a fairly normal main sequence star in its spectrum and temperature. Archival photographs added more controversy, with some analyses suggesting century-scale fading, while others questioned calibration across changing cameras and plates. Modern observations do establish variability across years, but the complete history of the star's brightness remains harder to reconstruct with confidence. The mystery owes its existence to citizen scientists, because an automated planet search might have ignored a signal this irregular and complicated. Human volunteers noticed that the pattern was not merely noisy, it was unusual enough to deserve years of professional follow-up. Later, amateur observatories joined major facilities, proving that a worldwide network could react whenever the star began changing again. Each telescope recorded only light, not photographs of the hidden objects, so researchers had to reconstruct reality from a moving shadow. A light curve is a one-dimensional clue, brightness against time, containing the speed, density, spacing, and transparency of unseen material. Saying it is probably dust does not finish the story, because nobody has conclusively identified the dust's source or architecture. Future dips must be captured simultaneously in visible, ultraviolet, infrared, and spectroscopic observations before the obscuring material changes or escapes. Those measurements could reveal grain sizes, composition, orbital distance, gas signatures, temperature, and whether the same structures ever return. The lesson of Tabby's star is not that astronomers discovered aliens, but that science was willing to test even an extraordinary possibility. An anomaly becomes evidence only when competing explanations make different predictions and observations repeatedly favor one prediction over the others. The light reaching us today began its journey around 14 centuries ago, long before modern telescopes existed to notice anything unusual. Whatever caused those immense shadows may already be gone, while Earth continues receiving an ancient recording written in fading starlight. So Tabby's star leaves us with a better question than whether aliens built something there. What kind of natural system can imitate them so well?